So mostly we've been concentrated in this chapter on unions, intersections, knots, Morgan's laws, and we also had subsets. Okay, so we're just going to have a little small section here, something called the Exclusion Principle. Now, funnily enough, I think this is when you get asked questions on this, you don't have to use this formalism. I think you'll kind of know it when you see it. But we'll just kind of do it anyway. Okay, so remembering that these bars mean the number of elements in the set when the set is finite, you have the following for any finite sets. That the number of elements in A or B is number of elements in A plus number of elements in B minus the number of elements in A and B. Okay, so I think how this works is probably something like this. Okay, so we'll take a universal set, and we'll take two sets A and B. A and B. Now I'm going to calculate three numbers as such. So we have this number, this number, this number. Okay, so how are we going to work here? Okay, I think what I'm going to do is I'm going to say that the number of elements in A is the number of elements in A without B plus the number of elements in the intersection. So the number of elements in A is basically 1 plus 3, the number of elements in A without B plus the number of elements in the intersection. Similar story, the number of elements in B is this bit, the number of elements in B without A plus the number of elements in the intersection. So I think what I'm going to do is if I add up these two, the number of elements in A plus the number of elements in B is equal to the number of elements in A without B plus the number of elements in B without A plus twice, because there's two of them, the number of elements, twice the number of elements in A intersection B. Okay, and so what this represents is number of elements in A plus the number of elements in B. And then what I have over here is, this is like 1 plus 2 plus twice by 3, the number of elements in there. So if I take away one of these, the number of elements in A intersection B, I'll be left with number of elements in 1 plus number of elements in 3 plus number of elements in 2, and that's exactly the same as the number of elements in A or B. So if I take away an A intersection B, you will find that this thing, take away A intersection B, is the same as number of elements in A without B, number of elements in A and B, number of elements in B without A, which is exactly the same as number of elements in A union B. And this is what's called the inclusion-exclusion principle. You can push this further and do it with 3 sets, but we won't worry about that here. So these questions, you can see they're actually quite easy to solve, and if you give us the answer, it's going to be fine. But I'm going to do it with this inclusion-exclusion principle. Okay, so let R be the set of red playing cards and P be the picture cards, King, Queen, Jack. Find the number of elements in R union P. So I'm going to write down that formula above the inclusion-exclusion principle formula. So the number of elements in R union P is equal to the number of elements in R plus the number of elements in P minus the number of elements in their intersection. Okay, so the number of red cards should be easy. So there's 52 cards in the deck. Half of them are red, half of them are black. So half of 52 is 26, plus the number of picture cards. So think of the picture cards. You've got 3 of them of each suit. There's 4 suits, so it'll be 3 of hearts, 3 of them of spades, 3 of clubs, and 3 of diamonds. 3 plus 3 plus 3 plus 3, 4 by 3, 12. But you must take away the number of red cards that are red and picture cards. And how many of them are there? Well, there's king, queen, jack of hearts, and king, queen, jack of diamonds. That's 6. And so you get 26 plus, 12 minus 6 is 6, so you end up with 32. Now, the question really is just, you don't have to explicitly use this, you can just find it. I mean, it's quite easy. Find all the red cards, and then all the picture cards that you haven't counted yet. Well, you've got the 26 red cards, and then there's king, queen, jack of spades, king, queen, jack of clubs. So you get 26 plus 6. The other thing is that you see here how where the double counting happens. So here, this includes, so if I just write down actually king of hearts, queen of hearts, jack of hearts, and we'll go back to the picture in a second, and we have king of diamonds, queen of diamonds, and jack of diamonds. So the 26, if you imagine it here, is the number of red cards, and these 6 cards are in the middle, and then B would be the set of picture cards. Now there's 6 of them that aren't red, the 6 black picture cards, and then there's 6 red picture cards. Now if we count the 26 here and the 12 here, we've double counted the middle, so we have to take away the 6. That's all the inclusion-exclusion principle says, really. Okay, so here's another one. Now, like, this is probably one that you can figure out on your own. I mean, I think the answer is clearly 2, but we'll see. We'll see. Okay, so let D be the set of drinkers and S be the set of smokers. Now, we're going to write down the inclusion-exclusion principle again. It would say that the number of elements in D, drinkers or smokers, is number of drinkers. Here, I presume the answer is 2. We'll just see what happens. Number of drinkers plus number of, I don't know why I have a P, it should be S for smokers. Smokers, take away the intersection, number of drinkers and smokers. Now, we're actually interested in the number of drinkers and smokers. So I think what we'll do is we'll just put in these numbers, and we haven't really got algebra yet, so let's see what happens. Okay, so now there's only 20 people, and they all drink or smoke. So the number of people that drink or smoke, that looks like a B, it should be an S, is 20. The number of drinkers is 15, plus the number of smokers is 7, minus the number that we're looking for, drinkers and smokers. And here you can probably just figure it out, because this is 22. We won't do any algebra here. 20 is equal to 22 minus number of drinkers and smokers. Well, how can you balance this? Well, the number of 22 minus 2 gives you 20. So therefore, the number of drinkers and smokers is equal to 2. Okay, not too hard. Now I've got a little thing here, but I don't think it's probably just confusing us at this time. There might be harder questions a bit further on. Yeah, there are these questions here. They're just kind of, if you want to push yourself. So if you're a bit struggling so far, you probably don't want to look at this too much, but we'll kind of go into it a little bit. So it's just about being precise with the notation, which is very important if you're a programmer. I mean, you have to be very precise with what you're writing in your code. So we may as well just see it in maths as well. You have to be precise. Okay, so X equal to the second thing, A, B, C, D. There's a difference between an element A in X and the subset, the set containing A, which is a subset of X. And then you can say that the set containing A is in the power set, because this is the set of subsets. These things are false. It's false to say that A is a subset of X, because this isn't a set. It's an object. You need to put curly brackets around it. It's incorrect to say A is in the set of subsets, because this isn't a set. It's incorrect to say that the set containing A is in X. It's not. The only elements of X are A, B, C, D, and none of them are the set containing A. it's incorrect to say that the set containing A is a subset of the power set, because like, okay, maybe if we write down the power set of this, it might help. Probably just write it down here, although there's 16 elements. There, we'll write some of them. So subsets of this. So we'll just go with, okay, the empty set, because remember, how do you make a subset? You ask the question, is A in it, is B in it, is C in it, is D in it? And the empty set is if you say no, 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 no. What if you say just yes to A and no to the others? Then you get the set containing A. Similar story, say no to A, no to C, no to D, but yes to B, you get the set containing B. You get the set containing C. You get the set containing D. You might say yes to A and B and no to the others. Now I won't put in the rest of them, there should be 16 in total. Maybe I'll just put in the last one. If you say yes to all of them, yes to A, B, C, D, that's the set X. Okay. Now a subset of this is a set containing elements of this. So this is not a subset, this is an element. It's true to say that the set containing A is an element of the set of subsets. It's not correct to say that the set containing A is a subset of this. Okay, you can write that the set, because remember, a subset is a selection of the elements from this. Now if you just say, oh, I'm going to pick this one, but it isn't quite precise enough because this is an element. This should be confusing, by the way. This is an element. So if you want to make a subset, you'll say no, yes, and then no to all the other ones. You can say, let's take the set containing this element. So you get the set containing A, and you can get in all kinds of confusion here, but this is a subset of P of X. So there's some questions to test you on this. It's probably harder than what we'll ask you. There's other things we can mess around with, is the empty set. So the empty set is a subset of every set, but not necessarily an element, but it can be. The empty set is an element of the power set. Bizarrely, the empty set is also a subset. If you choose none of these, yeah, you get there. And then there's a difference between the empty set and the set containing the empty set. Okay. If a set contains the empty set, then it is true that the empty set is in S. Okay. And then you can actually, so I probably said at the very start of this that you can kind of make all of maths with sets. So for example, you can make the natural numbers like this. So you can identify 0 with the empty set, 1 with the set containing 0, that's the set containing the empty set, 2 is the set containing 0 and 1, look, there's 2 of them, 3 is the set containing 0, 1, 2, 4 is the set containing 0, 1, 2, 3. And of course, what you can do is recursively define everything, not only in terms of sets, but in fact in terms of the empty set. So like the set containing 0 is the set containing the empty set. The set containing 0 and 1 should be the set containing the empty set, and 1, which is the set containing, and this should be very confusing. It is starred, which means you're not going to quite get questions on this level. Okay, now there's a few things that I've gone into that are not quite examinable. Just so you're clear, anything in general with that starred are probably questions harder than what's examinable. Okay. So now we're going to move into something that's brand new to you, even more than the subsets, is what's called Cartesian products.